Okay, yeah, thanks for the intro. So in this talk, I'll be discussing our recent work on DP-SCO, specifically with a focus on smooth losses and trying to maintain a single epoch of training with large batches. So let's start by just recapping the SCO problem. So in this problem, we're going to be given a smooth convex Lipschitz loss. For the purposes of this talk, we'll assume the smoothness and Lipschitzness values are constant. And then we're given a data set of n samples from some unknown distribution. And our goal is to choose the model theta in some convex set C that minimizes the population loss, that is the average of the loss function over this unknown distribution. So in addition to minimizing this loss, we want to do this with differential privacy. I put a formal definition up here, but you can just think of this as if I'm given two input data sets D and D prime, where they only differ in the contents of one sample, I want the output of my algorithm on these two data sets to be indistinguishable in some sense. And the way that we're usually going to do this is whenever we compute gradient or some gradient information about the examples, we're going to add Gaussian noise to it, and this gives us the indistinguishability we want. So the motivation for this work is that there's sort of a separation between the types of results that are optimal for the theory literature and the types of algorithms that we actually use in practice. In particular, there's like a number of properties that we would want an algorithm to have in practice that are not satisfied by the best previous results in the literature. So for this talk, we're just going to be focusing on methods that are first order and do some sort of batching. That is to say, in each round, the algorithm is going to receive a batch of examples. It'll compute a gradient or some information, some first order information on those examples, and then it'll use that information, make some updates. So the first property that we would want is that we want our algorithm to be single epoch, which is to say we want it to basically touch each example in the data set exactly once. This is important because this effectively means our algorithm is learning as efficiently as possible, and so it's scalable to large-scale data sets. The second and third have to relate with the privacy analysis. So there's results that show that if you form batches randomly, you can actually get better privacy. But forming batches randomly in practice is often difficult, whether it's because our data set is like large scale and we don't have the processing pipeline, or we're in a setting like federated learning where we have no control over how the batches are formed. Similarly, this third bullet point, there are results that can use convexity of the loss to show a better privacy guarantee. But we want to basically take whatever algorithms we develop in theory and then go ahead and turn around and use them for large models, which are often trained with non-convex losses. So ideally, we'd like our results to not rely on convexity for privacy. And then this last bullet, which will maybe be the main focus of this talk, is that often in practice we have some degree of parallelization, whether that's, for example, multiple GPUs or a distributed training setting. So we want our algorithm to benefit from parallelization as much as possible. So specifically, since we're thinking about a single epoch setting, for example, I could do n iterations with batches of size 1. But if I want to parallelize, I'd have to scale the batch size, which means I need to scale down the number of iterations. So for example, if I want to use a batch size of square root n, I need to use at most square root n iterations to preserve the single epoch constraints. So really what I mean by parallelizable here is I should be allowed to increase the batch size and decrease the number of iterations without making a sacrifice in utility. And for non-private algorithms, we know that this is possible. So if you look at the best possible non-private results for the SCO problem, we know that under the single epoch constraint, if I scale the batch size all the way up to n to the 3/4, there's no degradation in utility. But the previous private results didn't have this property. Basically, if the batch size was constant or near constant, they would get the optimal excess loss possible. But as soon as you scale up the batch size and decrease the iterations, their utility guarantees start to decay. So our main contribution in some sense is to effectively close this gap. So we give an algorithm where it achieves the optimal loss for DP-SCO, even if you scale the batch size up to n to the 3/4 and maintain the single epoch property. And in addition to getting this nice parallelizability property, we're also able to basically achieve all those other practical properties we wanted earlier, whereas most of the prior work in this problem sort of fell short in one of these areas. Okay, so that's basically the high-level view of our contribution. Now I'll try to give you some flavor of what the algorithm looks like. So the algorithm has three main components, and I'll go over each of those in a little bit more detail. So the big one is this notion of stochastic recursive gradients, which is a known variance reduction algorithm from the non-private literature. So normally the way that we compute gradients in an optimization algorithm is we just take the batch, we compute the gradient of each example in the batch, and then we'll just use the average and send that to some optimization algorithm. That's what SGD does. Stochastic recursive gradients do something a little bit more complicated. So what we're going to do is we're going to compute this delta term, So in round t, delta t is going to be t times the current batch gradient on the current model, minus t minus 1 times the gradient of the current batch on the previous model. So the way I've designed this delta t, it's if you sum up the delta t's, you get some telescoping sum. So in particular, if you do the math, and you can see that the average of the first t delta i's is going to, in expectation, be equal to the gradient of the population loss. So this suggests that we should use this average as our gradient in whatever optimization algorithm we're running. So why is this beneficial? I guess there's some variance reduction from stochasticity. I'm mostly just going to be focusing on the DP noise for this talk. So from the perspective of DP noise, we're able to show this key lemma, which basically says that these objects that we're averaging to compute the deltas each has constant norm, even though they have these t coefficients inside of them. And given this key lemma, that basically tells us it suffices to add noise on the scale of 1 over b to each of the delta i's. So this gives us a gradient estimator in each round, where the variance due to DP noise is on the scale of 1 over t times b squared, whereas if we just did something like DP-SCO, the variance would be on the order of 1 over b squared. So we get a reduction in the amount of DP noise we're adding, but the cost of doing this is that these delta i's are being reused across rounds, which means that the noise is also being reused across rounds. So this noise correlation makes it hard to show directly that this variance reduction gives us a benefit in utility. So we need to actually bring this down to something like 1 over t squared, and we'll see how to do that later in the talk. The second component of our algorithm is just accelerated gradient descent. I don't have too much to say here. Basically, since we're concerned about being able to converge in very few iterations, we needed a non-private algorithm with a very good convergence rate as our building block. The one thing I will say is we do need to do some extra work because now we're working with stochastic recursive gradients instead of standard gradients, but I'll leave those details to the paper. Okay, and the last thing we use is the binary tree mechanism. It's a tool from the private literature for computing prefix sums. So this is a problem where I have a stream of inputs x1 to xn, and I want to compute the prefix sums x1, x1 plus x2, x1 plus x2 plus x3, et cetera, with differential privacy. So the naive way to do this would be to privatize the stream by just adding Gaussian noise to each xi. But the problem with this approach is that if you look at the last prefix sum of x1 to xn, I have n noisy terms, so the variance of this prefix sum is going to scale linearly in n. The binary tree mechanism is just a clever way of adding noise, which allows my noise to scale polylogarithmically instead. And the idea behind it is pretty cool, but it's, I guess, not really our result, so I won't go over it here, but I'd be happy to talk about it in the poster session or at the breaks. So how do we use the binary tree mechanism? It turns out it combines pretty naturally with the stochastic recursive gradient idea. So recall that when we use stochastic recursive gradients, we're tracking these delta I objects, and then we're using the average of all the delta I's we've seen so far as our gradient in the current round. If you stare at this expression, this is exactly a prefix sum of the delta I's. So the idea is simply instead of independently noising each delta I, we're just going to use the binary tree mechanism to add noise to the prefix sums that we're using as our gradient estimates. And then this drives down the variance of our gradient estimates from 1 over t, from having a 1 over t dependence to a 1 over t squared dependence, which is enough to give us our desired utility guarantee. To give some bibliographic credit, this idea of combining the binary tree mechanism and stochastic recursive gradients actually first appeared in a previous work of Zhang, Tran, and Kukoski. But there's, I guess, a lot of technical differences in the way that we applied in our paper. Okay, so those are our main three components, and I guess what I want to do with the remaining time is give you some flavor of what the main technical contributions of the work are. So remember we had this key lemma that said that as long as our learning rate was set appropriately, the objects that we're averaging to form these delta I's have constant norm, which then tells us we don't need to add too much DP noise to them. So the way that we show this is basically if you do the math, you use Lipschitz smoothness, you use the way that we're updating the model, you can show that this thing is at most the Lipschitz constant, which we're assuming is a constant for this talk, plus the iteration number times the smoothness constant times the learning rate times the norm of the group population gradients. Okay, so there's two different ways that we handle this. So in the non-realizable case, that is the global minimizer of the loss function is not in the constraint set. The way that we handle this is we just set our learning rate to be 1 over the number of iterations, and then we just use Lipschitzness to bound the norm of the population gradients. And then this gives us the claim. But the issue here is that the learning rate is 1 over t, and usually when we do optimization, we want to set the learning rate to be something like 1 over square root t. So because we're using a smaller learning rate, we need more iterations to converge. So in this setting, we only know how to get the iterations down to n to the 1/2 instead of n to the 1/4. But in the realizable case, we're able to prove this key lemma holds even with a larger learning rate by showing that the norm of the population gradient is actually decreasing over time. So as this t term in my bound increases, the norm of the gradient is going to decrease, and so this bound is still constant. And the way we do this is pretty simple. We just appeal to smoothness. Smoothness tells us that the norm of the gradient, the population gradient at a current point, can be bounded by some function of the excess loss. And the excess loss is exactly what we're showing is decreasing over time. So that's the high-level idea, but there's, I guess, a lot of technical details that are needed to make it work, because now we've sort of introduced this circular dependence. We basically want to say our utility bound is good, which means that the gradient norm is small, which means that the DP noise we need to add is small. But we also need to say that our DP noise is small if we want to say that our utility bound is good. So we basically need to resort to an inductive proof where we sort of ping-pong between proving the utility is good and then proving that the amount of DP noise we need to add is small. Yeah, I think it's a nice picture, but there's a lot of gory details that go into this. Okay, so that's everything I want to say about our results, and maybe just to conclude with some future directions. So one thing is I mentioned that in the non-realizable case, our proof only gets our iteration complexity down to n to the 1/2. And we believe our algorithm should be actually able to get to n to the 1/4. We just don't know how. I think there might be some low-hanging fruit there. I think the other problem that maybe needs more attention is getting, I guess, highly parallelizable, or sorry, getting single epoch algorithms for non-smooth DP-SCO. So I guess even getting subpolynomial epochs would be interesting. And there's a partial progress. There are results that can do this, assuming some bound on the dimension. I think really what we want is a result that applies basically unconditionally. Okay, thank you for your attention.
Arun, questions?
I guess the theoretical result does assume we know what the Lipschitz constant is. I mean, if we were to use this in practice, what we would actually do is we would basically just tune the clip. We would like clip the object that we're actually noising and just tune that. So we don't view that as too much of a practical constraint, but it does require that knowledge to run.
Sorry, two things. One very basic one. What do you mean by realizable versus non-realizable for this one?
Yeah, so realizable here means if I look at the global minimizer, it's inside the constraint set. In other words, there's a point inside the constraint set whose gradient is 0. And we need that because if that point is like far outside the constraint set, the gradient norm could just be equal to the Lipschitz constant everywhere.
Cool, okay, that makes sense. Other question, it sounds like there's this nice connection between this like variance reduction as well as the binary tree mechanism, which has now seen 2 uses, I guess, in your work and the other work before. I'm curious, do you think there's anything more fundamental going on there? Do you think it's like a useful tool that might see use again? It seems pretty cool to me.
I do think so. I think like another place where it might naturally show up is if you look at adaptive optimizers, which sort of compute prefix sums of moments. I think there's some room to combine them better there. I think like I think there's some actually recent work that looks into this, but it does seem like a tool that's sort of anywhere where you care about a prefix sum, it seems universally useful, and it seems like that pops up a lot.
Right, I was going to ask if, like, say, it's been used for momentum or atom or something like that. Okay, but maybe we can chat about that offline.
Yeah.
Any other questions?